Hello, in this video I'm going to talk about contiguous memory allocation, and especially in context of a homework problem that you will most likely see on your next homework. So here's the type of problem. This is the end goal. The end goal is to figure out how this particular problem works. So the idea here is that you have your memory and it's been partitioned into different sized chunks or blocks. So the idea is you want to figure out which process should I assign to which block. And to do that, you need a little bit of background information. First off, what is contiguous memory allocation, some of the drawbacks, and some issues that you can run into, and then we'll talk about the various algorithms that you can use to actually do this selection mechanism. So first off, what's contiguous memory allocation? So there's two different ways that you can do contiguous memory allocation. You can use a fixed partitioning scheme where the partitions are actually a fixed size. So these are the partitions and they're fixed size. However, they don't all have to be the same size. So for the sake of this exercise, let's say that, I don't know, this is 8 kilobytes. This one is maybe 2 kilobytes, 4 kilobytes, 4 kilobytes, and 10 kilobytes. Okay, so these are fixed sizes. They're fixed at the very beginning of execution. And so now the question is, when processes come in, they're going to be assigned to these partitions. And they may be a good fit there, they may be a bad fit there, and we'll talk more about that later, but let's give an example. So for instance, we have, I don't know, let's have 5 processes come in so we can fill out each one of our spots. We'll have process A come in and it requires 7 kilobytes. Process B will come in and it will require 2 kilobytes. C, maybe 4 kilobytes. D, 2 kilobytes, and E will make 8 kilobytes. So these are all the processes coming in, so we can go ahead and assign them. So we'll assign A here, we'll assign B here, and C and D and E. Okay, so a few things to notice here. Now the first partition is 8 kilobytes large. But A only needs 7 kilobytes. So what we have is we have this empty space here. And this is 1 kilobyte that A is not actually using. So we have a little bit of empty space there. B we don't. C fits perfectly. D we have actually 2 kilobytes of empty space, right? So it takes up 2 kilobytes and our space allotted is 4 kilobytes. And then finally we have E that has 8 kilobytes and it's in a slot that is allocated 10. So again, we have 2 kilobytes that are empty. So I point this out because we're going to talk about it later. This is called internal fragmentation. And in general, that's really the drawback of doing contiguous memory allocation. Now, there's 2 different kinds of fragmentation, and we'll talk about it more in a second. The second way that you can do contiguous memory allocation is using a variable partitioning scheme. So in a variable partitioning scheme, I have this table here just, to make life easier in the next steps. But really what this is that as processes come in, spots in memory are allocated based on the size of the processes. So let's again write down those processes. What we had process A come in and need 7 kilobytes. B needed 2 kilobytes. C 4. D 2 kilobytes. E 8 kilobytes. Okay, so these are our processes coming in. So when A comes in, this spot in in memory will be allocated 7 kilobytes. So this block will be 7 kilobytes, and A will be here. So notice now there's no internal fragmentation with A. Last time we had 1 kilobyte that was left over, and now we have none. And the same with the rest of them. So B, this will be 2 kilobytes, C, 4 kilobytes, D, 2 kilobytes, and E, 8 kilobytes. So with this variable partitioning, we get the advantage that now we don't have any of that internal fragmentation. So that's good. So what is this fragmentation? I keep talking about it. I've talked about internal fragmentation, and that's, I guess, again, where the assigned space, so this is the assigned space, all of this is assigned to that process, that fragment. However, the process is only using this space. So all of this space left over here is unused, and another process can't use it because only one process can be assigned to a block. So this is internal fragmentation. There's also external fragmentation. So what's happening with external fragmentation is, so we have this, maybe this scheme here where some processes are assigned in this area, some processes are assigned here, and then we have these fragments, which are also called holes. And now we have a process come in here that needs 50 kilobytes worth of memory. So remember, this is contiguous memory allocation. So that means that it has to be all in one contiguous block. It can't be split among 2 blocks. So we see that we do have 50 kilobytes here, but it's split among 2 different blocks and is not contiguous, and so that's not going to work. So this is called internal or external fragmentation, where a process comes in that needs a certain amount of space, but there's not a hole that can fit that process into memory. So just to wrap up, so I kind of made a table here of fixed versus variable, why use one over the other. So you may be thinking, okay, so variable partitioning got rid of internal fragmentation. Great, so that means why don't we always use that? Well, it has a few drawbacks. So variable partitioning is usually difficult to implement. There's a little bit more of overhead for the OS. This is because now you're allocating things on the fly. It's always better to have a fixed size. It's always faster. And then it can also lead to external fragmentation. And so I'll give you an example of how this can lead to external fragmentation in the next slide. So for fixed, the equivalent advantages is it's very easy to implement, less overhead. However, we already saw that it can cause internal fragmentation. It can also cause external fragmentation. It limits the process size. So if you have those fixed blocks, if, say, the largest block in your scheme is only 10 kilobytes and you have a process come in that needs 20, now you can't field that process ever. It also limits the number of programs you can have in memory. So you have those fixed partitions, so you have a fixed number of partitions, and so therefore a fixed number of programs in memory. So variable, again, it solves some of those by, so it doesn't, of course, there's no process size limitation because it's on the fly. There's no restriction on the number of processes. Now I say kind of here because you will run out of memory eventually. You have this variable scheme where you can, field however many come in that you have space for, but at some point you'll run out of space. So it's not an infinite unrestriction, but it's definitely more than fixed. So an example of external fragmentation in a variable partitioning scheme is here. So for instance, you have, so the first time through, memory is unallocated, and it has picked up some processes, it's running, so it has run process 1 here, P2 is allocated here, P3 here, P4 here. We have some empty space here, and now P1 is done. So P1 is, this is now empty, and this is a block size of 2. P3 is now empty with a block size of 1. And let's imagine that P5 is waiting and it needs 3 megabytes. So again, there's 3 megabytes available. However, they're in non-contiguous spots in memory. So once you've done the variable partitioning, now without another mechanism, which we'll talk about in a second, this is now causing external fragmentation as well. Okay, so the 3 main algorithms for allocating these processes to partitions, so you have all these processes come in, you have processes in the ready queue, and you want to start allocating their memory needs into your RAM. So there's 3 main types. There's the first fit. So the first spot in our partitioning scheme with enough space, that's where we're going to put our process. So that's first fit. Then we have best fit. So best fit is the smallest hole that's large enough to fit our process. So we look through all of our partitions and we find the smallest hole that's still large enough to fit us, and we put ourselves there. And then we have the worst fit. So the worst fit, we choose the largest hole. And this might not be kind of obvious of why this algorithm is even there, but I'll talk about it a little bit at the end of where you might decide to use that. Okay, so here we go. So we're back to our very first slide. This is the end goal, right? This is what we want to be able to do by the end of this lecture. Okay, so let's do the first fit first. So here's our partitioning. So these are all of our partitions and their sizes. And these are the processes that are waiting. So these are waiting. Okay, and so now based on the first fit algorithm, we want to see where our processes, what partition our processes will be put into. Okay, so I'm going to go ahead and list 1, 2, 3, 4. And it's sufficient for these to write down the partition ID, which I've put as A, B, C, D, E, to assign which one will go to which. Okay, so process 1 is 123 kilobytes. It's first fit, so it won't fit into A because it's only 100 kilobytes, but it will fit into B. So 1 will be put into B. Okay, process 2 needs 323 kilobytes, so it can't fit into A. B is already allocated. It can't fit into C. It can't fit into D. Can fit into E. So 2 will be allocated to E. All right, process 3. Process 3 needs 523 kilobytes. So we can walk down through all of these, but you'll kind of, just at glancing at it, you'll find that there's no spots available that can field this request. So just to be clear here, let's see, process 1 is here and process 2 is here. So now process 3, I'm going to write it as null. It can't be ran just quite yet. Now we look at process 4. So process 4 needs 50 kilobytes. First one that we hit, A, is going to be fine for that. So we will allocate 4 into A. Okay, so that's first fit. Very first partition that we find that we can fit in, that's where we're going to be. So next, let's look at best fit. All right, so best fit, well, let's make one more comment here. So one more comment. So the first fit, we have a lot of internal fragmentation, right? So here, for process 1, it's only 123 kilobytes. So there's actually a lot of space here in B that's not being used. So 1 would really be just down here. So this is an issue, but we'll come back. Okay, so best fit. Best fit, again, we're going to look for the smallest partition that's still large enough to fit us. So I'm going to, again, write down all of my process IDs. And let's start looking through here. So the first process is requires 123 kilobytes. So we're going to scan through here. This one's not large enough. This B is large enough, but we continue to look down through the rest to see if we find a better fit. So here we would have, so if we looked at for B, I'll do this calculation for one of them. So for B, this would be 500 minus 123, which what would be 477? Yeah, 477, so that would be 477 left over. If process 1 was allocated to C, we would have 200 minus 123, which would only be 77. If it was allocated, so this is if it's allocated to B, let's change this. If it's allocated to C, if it's allocated to D, we will have 300 minus 123, which is 177. And if it is E, then we will have 600 minus 123, which is, what, 577? You guys are supposed to tell me when I make math mistakes. You guys are falling down on your... All right, so fine. 377. Yes, and 477. Okay, first math error. I'm going with it, though. I'm not re-recording this. Okay, so here we go. Now we look at the leftover space for each one of these processes, and we see that the best fit is going to come from if we put it into C. So this is obvious when we're looking at it, but I just wanted to go through the calculation just for one of them, just so we can see how this would work in a system. Okay, so one is going to be allocated to C. I'm going to erase this for now. Okay, so let's look at process 2. Process 2, 323. That is going to be best allocated in B. Okay. Now let's look at process 3. That is going to be best fit into section E. And 4, its best fit is going to be in section A. Okay, so this is the algorithm for best fit. So there's one more remaining. So notice here, if you can flip back between the last one that we did and this one, and you'll see that we have a whole lot less internal fragmentation. So this is good. This is so far so good for internal fragmentation, minimizing that. Okay, last one is the worst fit. So the worst fit here, we're going to just take the largest possible remaining slot, and we're going to put our processes there. So process 1 comes in with 123, and so we're going to find the largest spot, which is E, and we're going to put it there. Process 2 comes in, 323, we're going to find the largest spot, which is B, and we're going to put it there. Process 3 comes in. Process 3 we can't do anything with. We don't have any spots to put it, so I'm going to put it null. And process 4 comes in with 50 kilobytes. Doesn't really matter. We're going to just choose the largest one. And so this is going to be A. I'm sorry. Back up, back up, back up. Erase, erase, erase. This is going to be D. Okay, so this would be the worst fit. And so what probably I would hope you guys, somebody would ask in class is, why would you even consider doing something like this? This seems like a terrible, terrible, terrible strategy. So it does have an advantage. And in the next slide, so there's this technique called memory compaction. And so it's kind of summarized here in this chart where you have all of this, so these are processes being allocated, running, and at this point process A has stopped. Now there's a big hole in the execution here, And maybe, so in this next spot, so D comes in and is able to fill at least partially part of that hole, but now we still have this hole here. So to get rid of that hole, we can compact our memory down, just like a trash compactor. We can compact it down so that we don't have any holes anymore. So if, for instance, we have this kind of partitioning where I don't know, maybe this is, okay, Casey, you don't have enough space to write over there. What are you thinking? Do it here. So maybe this is 4 kilobytes. This is 8 kilobytes. I don't know, 2 kilobytes. We're gonna ignore that is larger than the other one, and this is maybe 10. So imagine that we have a process come in and it needs 2 kilobytes. So we have P1 that needs 2 kilobytes. So maybe we put it here. I'm sorry. Let's choose to put it here. So we have P1 executing here. For whatever reason, maybe the rest of them were taken. So P1 is executing here. It's only taking up 2 kilobytes. So we have still now 6 kilobytes left over. And so now let's imagine, well, let's change one thing. My example is falling apart. So let's make this 8 kilobytes. So now, we have 6 kilobytes left here. This is 6 KB. And let's now imagine that these become allocated with something else. Now if we have a process come in that needs okay, my example is not going to be the best, but I'm going to continue with it anyway. So if now we have a process come in that needs 10 kilobytes, we don't have it right now. Right now we have these two, we have a 4 kilobyte and 8 kilobyte here, but process 1 is only taking up 2 kilobytes. So really we have a hole here and we have a blank spot here. So what we can do is we can compact things and repartition such that now I can free up this 6 kilobytes and I can now have a partition here that's 10 KB that can field our mystery process that comes in with 10, needing 10. So worst fit can kind of help in that. So here I allocated P1 based on the worst fit, where I just chose the largest one. It's going to leave a lot of extra space, which can come in handy through this mechanism of memory compaction. So that ends the lecture on memory, contiguous memory allocation. The next ones that I will start to record are based on paging. So we'll talk about paging next. Let me know if you have any questions. Thank you.